Hello everyone, I am Shagotam Pal. I am going to give you a lecture on Introduction to Fracture Mechanics. Now, today we are going to discuss what is fracture and types of fracture, fracture mechanism, atomistic level, and modeling of brittle fracture with the Griffith criteria and stress intensity factor, and modeling of ductile fracture with the help of J integral, and fracture mechanics and its application to design of material. Now, what is fracture? Fracture is a separation of body into pieces due to stress at temperature below melting point. And what is fracture mechanics? It is a mechanics of crack generation, crack propagation, and creation of new surfaces, which leads to the final failure of material. According to the load, the mode of fracture can be three types: mode 1, mode 2, mode 3. Mode 1 is load is in plane and load is perpendicular to the crack propagation plane. Mode 2, in plane loading but parallel to the crack propagation plane. Mode 3 loading, it is out of plane loading and parallel to the crack propagation plane. Now, if we classify the fracture, we can classify it in three ways. One is strain before fracture, crystallographic mode, and fracture appearance. Basically, fractures are two types: ductile and brittle. In the ductile fracture, if we see the crystallographic mode, ductile fracture is related to the void nucleation and growth, and brittle fracture is related to the transgranular, where crack propagates between the grain, and in some cases crack propagates in the grain boundary. So, as ductile fracture is related to void nucleation and growth, the fracture surface look like fibrous and brittle fracture surface look like granular. Now, what is the fracture mechanism in atomistic level? We all know that material consists of atoms. When two atoms are really close, the both atom will start repulse to each other. This repulsive force will decrease with the distance between the atom, increasing distance between the atom, and stabilize in an equilibrium point where we can say that in equilibrium point the distance between two atoms are x0. If we further load, then what will happen? The attraction force will decrease, and this force displacement curve or force displacement can be graphically represented by half of sine wave, and from the equilibrium point to any point of x distance we can get the load with the expression of maximum load, the cohesive force, and sine of pi x by lambda, where lambda is the half of the sine wavelength of the sine curve. And as we know that load is proportional to the stress, then directly proportional to the stress can also be written as this form, where x is very small. So we can rewrite the stress is sigma 0, sigma c pi x by lambda. Now, if we increase x distance, then the strain will be x by x0, and stress is E into x by x0. E is Young's modulus. Now, if we relate this equation, these two equations, we can get the sigma c is equal to E of E lambda by pi into x0. Similarly, when we want to break the bond, we actually break the bond energy. The energy between bond energy is the actually bond energy is a integration of 0 to lambda sigma c sine of pi x by lambda dx. It is the bond energy. And when we want to create surface, when a crack propagates, there will be two surfaces, creation of two surfaces, generation of two surfaces. So if surface energy, the required surface energy is gamma s, 2 gamma s will be the bond energy equal to the bond energy, and here we can get that lambda is equal to pi gamma s by sigma c. And from this equation, if we replace the value of lambda, then we can get the final form of sigma c, that is equal to E root over of E gamma s by x. Now we know that fracture is two types. One is brittle fracture, one is ductile fracture. So in the case of brittle fracture, we consider that there will be no plastic deformation. Plastic deformation is one irreversible process. If there is no irreversible process, then the total energy can be written from the first law of thermodynamics, that potential energy and external work done, that is also constant. So the energy release rate, that will be 0. That energy release rate means the energy release rate due to potential energy and creation of surfaces. So potential energy U is the current potential energy, and U0 is the undeformed potential energy. So potential energy can be written U is equal to U0 minus pi a square sigma square b. B is the thickness of the specimen and E is the Young's modulus, and we can get this energy release rate potential in terms of potential energy by this equation. And similarly, the surface energy, how much work is needed to create two surfaces, that gamma is for creation of one surface, that means the unit surface, the energy per unit surface. So in a area is 2ab, so total work required, so that energy release rate for this work done, that will be and that will come to the equation dws by dA, that is equal to 2 gamma s. So we know from this equation, we know that minus du dA, that is equal to dw ds. So if we equate these two equations, we will get a expression of sigma in terms of A, finite crack length A, and surface energy. And here sigma c, if we put sigma c is the critical stress, then we will get 2e pi ac, 2e gamma s by pi ac. That ac is the critical crack length, and here sigma is the far field stress. This is Griffith energy criteria, energy release rate. Griffith criteria, energy release rate for modeling of brittle fracture. Now we can model the brittle fracture in terms of stress also. Here, if we apply some far field stress sigma, and if we consider a point that is distance from crack tip, r distance from crack tip, and the joining line of point and crack tip, if it is the angle between the joining line and the x-axis, horizontal axis is theta, then sigma xx can be written as this form. Sigma y can be written as this form, where K1 is stress intensity factor. Stress intensity factor. So what is the stress intensity factor? Stress intensity factor is a parameter to describe the stress scenario of the crack. And if we put theta is equal to 0, then sigma x and sigma y becomes ki by root over of 2 pi r, depends upon the r value. The sigma is depending on the r value. And if we measure at the crack tip, that means r is 0, then sigma will become infinite. Sigma will become infinite. Sorry. So there will be a singularity condition. And this sigma x and sigma y is related to far field stress. So K1, the stress intensity factor parameter, also can rewritten with the in terms of sigma far field stress and finite length of crack, that is K1 is equal to sigma into root over of pi b. Now this is also stress intensity factor approach is also applicable for brittle fracture only, where there is no plastic deformation at crack tip. Now if plastic deformation is present, Rice introduced one J contour integral method to model the ductile fracture. Basically, around the crack tip, gamma is an arbitrary path around the crack tip. J integral is defined as, it is a integration, basically integration of strain energy and traction. Strain energy and traction. Ti, here Ti is the traction component and ds is the small increment along the path. And here we can see that this is also an energy approach, and it is the J parameter is like Griffith energy release rate, it is equivalent. And here this J is path independent. So what is meaning of path independent? The value of J for one finite crack is path independent. It is not dependent on the path. So this is the mathematical representation of ductile fracture parameter. Now we are going to study how to apply fracture mechanics in design. We in the design field we have only load and crack opening displacement. Here we can see the load is non-linear at some point. So this load non-linear means there will be some plastic deformation. So we have to calculate the J. how J total J can be separated into two parts, J elastic and J plastic. Now J elastic portion, for the elastic portion we know that we can calculate a K, and K is directly proportional to far field stress or load, and also some geometric function, that is A is equal to the crack length, W is width, D is the thickness. So K can be computed with this according to this formula, and from the K we can calculate the J elastic portion, where E is the Young's modulus and mu is the Poisson's ratio, and J plastic can be calculated from the area under the curve, plastic area under the curve. If we put a line parallel to the initial slope, we can segregate the plastic area, and if we know the plastic area, we can calculate the J plastic. Eta is the geometric function. B0 is W minus A, that means uncracked ligament, and Bn is B. So we can calculate the total G, and from this equation we can calculate the equivalent fracture toughness, how much energy per unit area is required. What is fracture toughness? Fracture toughness is a quantitative way of expressing a material's resistance to crack propagation. Basically, we need a safe model, fail-safe model, where we can be sanguine that there will be no further crack propagation. So, fracture toughness is for the brittle material, fracture toughness is a number, and if we have two loading paths, sigma 1 and sigma 2, and the initial crack length A0, we can actually make a statement that whether sigma 1 or sigma 2, what is in the unstable zone or what is in the stable zone, because if further crack goes, sigma 2 that falls in the unstable zone and sigma 1 falls in the stable zone. In that way we can decide what is the failure load, what should be the load. And similarly for the elastoplastic, we can get the resistance curve, and we can see that this is non-linear curve, and the same way we can get the instability point. Now this failure, we can introduce this fracture mechanics in the design in terms of failure assessment diagram. Before going to the failure assessment diagram, we should know how material fails. Material fails in mostly two ways: plastic collapse and fracture, and combined plastic collapse and fracture. When the plastic collapse, what is plastic collapse? Plastic collapse is when the ratio of stress and the material yield stress becomes more than 1. Then this condition is plastic collapse. And when fracture, the ratio of stress intensity factor and effective stress intensity factor becomes more than 1, then we can say it is completely fractured. So we can make a diagram where a boundary layer, where what is the safe zone and the unsafe zone. If we consider a design zone, if the design point is out of this failure assessment curve, then we can take a decision that this design point is unsafe. We should not go for this design point. And this failure assessment diagram if the fracture is if the failure is fracture dominated, that means Kr value is nearer to the 1, and fracture if the failure is plastic collapse dominated, the LR value is nearer to the 1. In that way, we can get the failure assessment of a component of a system of mechanical deformation system. Thank you for listening to my uh, listening lecture, and hope soon set of detailed studies of fracture.